Welcome to today's lesson, the very first example of a real full hypothesis test. Because of that, it's going to be a longer than normal example, which I apologize for. If you don't already have printed out the 6 steps for hypothesis testing, I encourage you to have those printed out. You'll see the short version of those here on the screen, along with information about interpreting in the context of a claim, which we'll come back to. But again, we'll go through these 6 steps for this first example. You hopefully already read the example here about newspapers. So it mentions a significance level, so we know it's a hypothesis test. So we start with our hypotheses. We ask ourselves, what parameter are we testing? And basically your choices are mean or proportions. And in this case, it's proportions. Usually the lots of percentages give you that hint. And then you ask yourself, what percentage, what proportion are you testing it against? And the newspaper is claiming that it's 5%, so we're going to test it against 0.05. Make sure you write 0.05 and not 5%. That can get you in trouble. And then how are you testing it? Look for, sometimes these exist, sometimes they don't. Look for inequality phrases, less than, at least, at most, greater than. Sometimes those will not exist, and we'll see examples of that later on. But in this case, the number that is against the 5% is at most. Now, at most means less than or equal to, and since it has an equal to, it goes in the null. If it did not have an equal to, it would go in the alternative. And that's what they are claiming, so we'll label that as the claim. The opposite of less than or equal to is greater than, so that will be the alternative. Please note that your textbook uses equal to every single time for the null hypothesis. I'm fine with you doing this. I just want you to be able to recognize that if someone does less than or equal to, that's also the same thing. So be comfortable with either one. The second step is to determine the tails and the distribution. Since it's proportions, it's a z distribution, that is a standard normal distribution with a mean at 0 and a standard deviation of 1. And to check which tail it is, look at the alternative. It says p is greater than. So hopefully you recognize that greater than is on the right. Numbers that are greater than are on the right side. So I'll shade the right tail. And then because this is a z-test, I'll label this with a z. If it were a t-test, I'd label it with a t. Step 3 is the test statistic. And you have different formulas for proportions. Your test statistic is called z because it's a standard normal test. And you have this very ugly formula. If you prefer, instead of q, a lot of times I'll write 1 minus p. Those are exactly the same things. Note that in this denominator, there are no hats. And I point that out because it's similar to a square root that you saw back in chapter 7 where you did have hats. But we do not have hats here. So this formula has basically 3, because again, q is 1 minus p, basically 3 numbers. I always like finding n first. I find it to be one of the easier ones. And a lot of times I need n to find p hat, so I'm going to have to find it first anyway. In this case, we sampled 200 newspapers. P is a parameter. Whether it's p or mu or sigma or something else, the parameter always comes straight from the hypotheses. And this is the one place where it might be helpful to go back to the null and think about it as equals and not less than or equal to. And if I'd written it that way, then the null would be p equals 0.05. So that's what we're going to plug in for p. P hat. Sometimes p-hat will be flat out given to you, and other times you'll have to calculate it. In this case, you have to calculate it. It says 16 of the 200 newspapers had printing errors, so 16 divided by 200. Now, you may absolutely leave it as 16 divided by 200, and for a few of you, that might be easier. Personally, I find it easier to convert it to a decimal. In this particular instance, it's very nice because it's a very nice number of 0.08. But if it's not a very nice number, you still may want to convert it to a decimal, and I'll show you the one thing that you really have to watch out for when we get there in a minute. So we plug in all of these numbers. One thing I'd like you to pay extra careful attention to is the numerator of these test statistics. For the ones that we're going to do in 8.2, 8.3, and 9.3, the numerator is going to be the key for telling you, is your test statistic positive or negative, which is extremely important for two-tailed tests, which this is not a two-tailed test, but also extremely important for you just to use as a basic check of your work. In this case, you should be able to note that 0.08 minus 0.05 is a positive number. So my test statistic, whatever it is, should be positive. So let's calculate it and find out. So we calculated a moment ago p-hat, and I said it was the very nice number of 0.08. Let's confirm that. It was 16 divided by 200. 200, not 20. And there's the 0.08. N was 200. P we said was 0.05. So to plug all of that in and calculate the test statistic, we have equals. Here's the one thing that is not super important on this question, but if you did not have nice numbers would be. Notice that I'm clicking on the 0.08. I'm not typing 0.08. Anytime you don't have a nice number, it's very, very important that you cell reference it. Minus the 0.05 divided by squirt of 0.05 times 1 minus 0.05 divided by 200. So we get approximately 1.95. Notice we got positive 1.95, which is what we did predict. In these three sections, most of the time, not all of the time, most of the time your critical value, your test statistic should be between -5 and 5. It's probably going to be even between about -4 and 4, but I'll play it safe and say -5 and 5. If you get a test statistic of 27, for example, please double check that. I'm not saying that it's wrong, but I'm saying it warrants you going back and making sure that you typed everything in correctly. So 1.95 seems like a nice number. Again, it's positive. It's between -5 and 5. So all of that feels good. Step 4 is the p-value. Please note that this is capital P. Now, there are, depending upon how you want to count, there are 3 or 4 possibilities for how you could actually, I guess, double that, possibilities for how you could calculate the p-value. There are several things you need to consider. The one that is most often missed is to look at the tails of the test. We have a right-tailed test. That's what we said in step 2. When you have a right-tailed test, if you think back to chapter 6, when we were calculating the shaded region on the right, we had to use the complement rule because the dist commands in Excel only gave me the area to the left. So since this is a right-tailed test, we will have to use the complement rule. So we'll use 1 minus. Another thing that you have to consider is which distribution is it? This is the Z distribution or the standard normal distribution. So we're going to use 1 minus norm.s.dist. You may, of course, use just norm.dist where you remember to put in the 0 for the mean and the standard deviation for the 1. So we have 1.95 is where our mark is. And then, of course, I've told you before in this class, we always use true. We have 1 minus norm.s.dist. And again, make sure you cell reference the 1.95 since that was not exact. And we get 0.0258. Now this 0.0258 represents the probability that if in fact the advertising was 0.05, or the printing errors was 5%. If that was true, the probability that a random sample of 200 would have 16 printing errors or 8% printing errors is about 2.5%. So that is a fairly low percentage. Specifically, it is lower than the significance level of 0.05. So in other words, that's unusual. So we're going to say, you know what, that's so unusual that we don't believe what they're saying. So we reject that null hypothesis. And your interpretation, your book provides a good interpretation, but it's just not my favorite. I'll use it when we get to section 9.3, but for the next few sections, I prefer to do something else, and I prefer to do it in 2 sentences. So start with the significance level. That's the one thing that you need to include that doesn't make sense to the typical person, but it should be there. Just like when we were interpreting confidence intervals, you would say we are 90% confident. You had to state that confidence level. So we have to state the significance level. So we conclude that the. Now in this case, we were testing proportions. So you need to use the appropriate word of either proportion or percentage. Generally speaking, you can use either one as long as your numbers match the word you pick, and I'll come back and talk about that in a minute. Later on, we won't use proportion or percentage, we'll use the word mean, okay, or whatever parameter we were testing. So we conclude that the percentage, so for proportions, now talk about what you were measuring. We were measuring printing errors. So the percentage of printing errors. And then all interpretations should talk about the word all what. In all. This next one, a lot of students find helpful, but a few students find confusing, and I apologize if you're finding confusing. I like to think about in here. In was 200 what? 200 newspapers. So we say the percentage of printing errors in all newspapers. The one bad thing about thinking about in is you should never in your interpretation mention the 200. Always use the word all. So in all newspapers. And then your interpretation is going to focus on what was your decision. We in step 5 chose to reject the null. If you choose to reject the null, you should sound very confident in your answer, sure of yourself. If you fail to reject the null, which should already sound like a very wishy-washy statement to begin with, then your interpretation should sound very wishy-washy. And we'll do an example of that later on. But in this case, we're rejecting the null. We should sound confident. So you're going to say is, or was, or will be, depending upon the tense. In this case, is. And it's not 5%. When you reject the null, it may be helpful to think about what you're saying is that H1 is, again, I'm sounding confident. You're saying H1 is true. So H1 was greater than 5%. Now, I mentioned a moment ago that your words had to match your numbers. I use the word percentage, so I am forced to use the number 5%. If I chose the word proportion, I would need to choose the number 0.05. You can't mix up and go back and forth. So they do need to match. I really like this sentence because I think it does a good job of telling you what you proved. But your book is very insistent that you always talk about the claim. And this company claimed that there were at most 5% errors. And what we proved was that that was not true. And this is where I'll go back to, we had the claim in the null. So we're in the first column, and we rejected the null. So we're in the top row, which would mean this is what we have learned about the claim, that the claim is false. And again, it sounds confident. If you look at the one right below it, it says could be. Sounds very wishy-washy. But we're saying that the claim is false. Now, the only thing you need to do to explain that more is to state what is the claim. So the claim that the percentage is at most 5% is false. So that takes you through completely one set of hypothesis tests. It will be slightly different for means. It will be slightly different when you fail to reject the null. You could argue that it's slightly different depending upon where the claim is. So things are slightly different from one problem to another. But this gives you a fairly good gist, and a few more examples would give you an even better gist. As always, if you've got any questions, please feel free to email me.